One point that remains memorable for me from yesterday is that we discussed again that we discussed this very simple model of a particle on 5 sides, and we established the detailed balance condition. And I think it was no earlier than yesterday that we actually showed that it was exactly valid. Right? There was absolutely no approximation made. So of course we have an approximate. I mean, we have a stochastic process which has its noise, but the underlying laws are completely fixed. So should I start? Should I start? So good morning, everybody. I hope you're doing well, not soaked too much and not too much touched by the different viruses that are running around. So today I want to discuss lifting and lifted Markov chains, which is another chapter of the modern ideas in what I would consider modern ideas in Markov-chain Monte Carlo. And what you will see today is that in huh? It's yes, it is recording. Yes, yes. So so this is what I'm going to talk about. So it will illustrate it will illustrate what I consider being creative ideas in the field of computational physics. But of course, in order to get our inspirations, we always have to go back to simple models. So there will be a connection to one-dimensional systems and to the physics of interacting particles in one dimension, in particular the SEP and the TASEP. So let us. I think I don't have to rewrap everything. We understood that we have 2 conditions that we can satisfy. The first condition is the global balance condition. Pi is equal times pi p. That is the global balance condition. Balance, and in all what I am discussing, I'm only discussing exact algorithms. So I'm discussing exact algorithms. So sometimes in the early days, I got into trouble in my department because there are lots of people doing exact calculations. So when I announced exact Monte Carlo algorithms, and they said I was taking things too far. But exact means that we actually satisfy this condition. So that is the global balance condition, and then so that you can write as A sum over B BA. And then we have the detailed balance condition, pi A PAB is equal to pi B PBA, which is the detailed balance condition. I think we have understood that these are 2 the conditions. We have understood, did we understand that this implies that one? Did we understand that the detailed balance condition implies the global balance condition? Maybe we have understood. So now, for many decades, this global balance condition played absolutely no role. Of course, not for us, because yesterday we were happily programming with help of Gabriele. We were happily programming the zigzag algorithm, which is clearly a global balance algorithm. But we'll go into more discussion. So the field was, in some sense, that I'm discussing here of lifted Markov chain, lifting. It's not liftling, but it's lifting, but lifting. So was founded about 25 years ago by considering a simple particle moving so here we have L sides, single particle. So I'm just doing the random walk again in one dimension. So now what I can say is I have a particle which is at a position x, let's say xt, and I call this xt, which is an element of the sample space of the random walk, which is simply the path graph from 1 to L. So now we can, and the algorithm of course, now it can move with probability, for example, 1/2 to the right, probability 1/2 to the left. Maybe it also has a probability to stay where it is. That's all not so complicated. And we all know that we expect a tau relaxation time, an inverse gap of the transition matrix, which is 1 over L square, which means that it will take our random walk, it will take it L square steps to move through the lattice. And yesterday, after you came back from karaoke, maybe you realize that when you don't know exactly where you are going, you also have increased time scales. So that is kind of normal. So now we can do a very simple, extension of this concept, and that goes back to a paper that I already cited, Holmes and Neal, 2000. There's a foundational paper where they said, well, let us lift this chain, this configuration into 2 configurations, check. So I have this configuration and saying I'm making it into a right turner and a left turner. So for example, I can do this with so I want it like this. So now let us make new rules. So now we write, so that we call this here xt in the omega of the lifted random walk. So this is, we will do a lifted random walk. And what will this lifted random walk do? Well, first of all, I don't introduce periodic boundary conditions because that would simplify the problem too much. So now I have x is, so here I had just a position x. So xt is in some sense an index here, and here I have xt is an index, and here I have xt is an index plus a sigma variable. So I have one more variable. And now what I'm doing is the following. In the bulk, so for example, I have this configuration here, which is I sigma is equal to -1. So now I do the following. I move, so this is the configuration xt out of omega lifted random walk. And I'm just simply move it to the left. So many of these things will not surprise you. Okay, so I move it to the left. But then I have a probability alpha. So where I want to get with you is to show how general, so is 1 minus alpha. So now with probability alpha, I turn my spin around, and with probability 1 minus alpha, I just leave it where it is. Okay, so this is kind of easy. So what I'm doing, some people say I'm introducing momenta. So I'm introducing momenta, and then with the probability alpha, I turn my momentum around. So that is in the bulk. And now let's do the same thing at the boundary. So for example, we are at the boundary. Check. We are here. So this is our configuration at xt. So this is xt plus 1 out of omega lifted random walk. And now we are at this configuration. Now what we do, what would be a good algorithm for this random walk is with probability p equals to 1. So of course we could do periodic boundary conditions, but this is not what we are interested in. We are looking for la petite graine, as we say in French, the little thing that makes, little grain of salt that makes things interesting. So we're looking for the little grain of salt that makes things interesting, and that's exactly that we have that we have hard wall boundary conditions. So here with probability p equals to 1, what we do is we return the spin, but so this is xt out of omega lifted random walk. And then what we do is the following. Is now with probability alpha, what do we do? I mean, what should we do? Are you all right? This is pointing right. So now, here so we had the first step. So we had the first step here that we moved to the left. And we couldn't move to the left because there was a hard wall. So instead of moving to the left, we turned it around. So now with probability alpha, what we do is we turn it around. Okay, so with probability alpha, we turn it around again. And with probability 1 minus alpha, we leave it where it is. All right, so now we can do that. So now that looks completely ridiculous, right? Who would ever write a paper on this? But then, of course, it's the generalization potential of ideas like this that can found a whole field. Now, what do we have to check? We have to check that this so we are trying to have a random walk. That means every configuration has the same weight. We have broken up the configuration into each configuration into 2 lifted configurations. So what we would like to have is that every lifted configuration has the same weight. And if you listened carefully yesterday, then you notice that there is a little principle, is we write down the transition matrix and check that it is doubly stochastic, right? If it's doubly stochastic, then, and you know, it's kind of a little pleasure that we shouldn't avoid. So especially on a morning at 9 o'clock. So let's take one single particle. Let's take configuration 1. Let's configuration 2. Configuration 3. What would it be? What would it be? This one. What would be configuration 4? I'm not going to do the whole gory detail here. Okay, so right, you see that we can write this configuration. So now, what is the transition matrix of the lifted random walk? We are not going to write down the whole thing. But how does it start? From 1. So, come on, yesterday you were so helpful. You were so incredibly helpful with me at the blackboard. So from 1, where can we go? Excuse me? 2? No. 1 is like this. So then I go here. Huh? I go to 3. Yes, so what is the transition matrix element? So 1, 1 is 0. Okay, you agree with that? So what is, come on, we have lots of things to do. I have 17 pages to do with you. And Filippo told me I'm allowed to keep you until everything is done. So, okay, so let's go. 1 times alpha bar. Okay, I go to 3. Now, because this is not, see, that's why these things are helpful. This is not configuration t plus 1. That is configuration t plus 1. Okay? So I go 3 with alpha bar, 4 with alpha. Okay, so I have this here, that corresponds. And now let's do 1 here from 2. That's from 2. So 2, where do I go? I go to 1 with probability alpha bar, and then I go to 2 with probability alpha. Okay, and so on and so on and so on. And I can assure you of the following, that this, let's do here, let's element 4, let's just for your fun, I do it here, alpha bar. So now what you will see is that that the rows of this transition matrix sum up to 1. That's not surprising, because it simply means that we go somewhere after time. So it's a real random walk. It's a real random walk. It has no probability to stop, and it goes down here. So we have a doubly stochastic matrix, and it satisfies the doubly stochastic matrix means that it is that it's stationary distribution. So doubly stochastic. And it means that that pi is equal to 1, 1, 1, 1. So let's do the following. Maybe if you don't mind, let's do the following. Let's write down the transition matrix, and then we will observe something. Let's write down the transition matrix of the random walk with configuration 1, 2, 3, and 4. Let's do this rapidly. So I think from 1 we go with probability 1/2. We go to 1, and then we go to 2. From configuration 2 we go to 1 and 3. Okay, and so on and so on. So now what I want to show you is that this transition matrix that we just wrote up here, so here we have an element 1, 1. Here we have an element this. Here we have an element like this. And these elements, you find them exactly back here. If you write little blocks, two times 2 blocks, you see that the element 1 becomes an element chak chak alpha bar. The element 1 up here becomes an element alpha bar, alpha 0 0 and 0 0. So this transition matrix is doubly stochastic. It's non-reversible. It's a non-reversible transition matrix. And basically, it's the same transition matrix that we had before. So P L R W is some kind of, has a very close relationship to the transition matrix of the random walk. All right, so now, so that's something that we will find back again. And now, for correct choices of, for a good choice of alpha and alpha bar. So in fact, if you choose alpha is equal to 1 over n, alpha bar is equal to 1 minus 1 over n, you'll find that tau random walk, lifted random walk, is like L. So the relaxation time of the random walk was come on, I mean, you got into the habit of correcting me. You know, I think that was a very good habit. So, you know, just keep this habit. So the inverse gap was L square. Here the inverse gap is L. And I could go on for a long time discussing how this comes about. So that's very interesting things happen on the level of the of the transition matrix of this this object. But now let's move on to something more. Okay, that's clear what we're doing here. So that's what I was telling you was the content of the paper by Diaconis, Holmes, and Niels from 2000. So by simply lifting our configuration from 1 into 2 and generalizing, you obtain a transition matrix which on a coarse-grained level is exactly the old transition matrix, but it has much faster relaxation time. Now let's do the same thing, not for a single particle. Okay, unless there are questions. Yes. So it can remain a square. So there is some fine tuning involved, but there's some fine tuning that I won't go into detail. But so there is some fine tuning parameter which allows you to get to go between alpha square and alpha. In fact, the only value where you have L square is the value where alpha equals to 0. And we can discuss that, but it would take me too far. We can discuss that on the level of the transition matrix. So in fact, what's happening, but let me just tell you, because the transition matrix of a reversible algorithm, just like the random walk, is a real matrix with a real spectrum, and the eigenvalues are an orthogonal set of the eigen. So then the real eigenvalues start to move on the real line, and at some point they go into the complex plane. And at that point, you have the optimal operation. But now let's do something. Let's discuss a much more complicated system, which is called the symmetric simple exclusion process. So it's called a process because it is discussed usually in continuous time, but we will stay in our world of Monte Carlo algorithms where at each time step we make a single move. So now let's do this. And so it is exactly the same model with the difference that instead of a single particle, we have many particles on a lattice. So we have 1 to L. We have n particles on our lattice. We may have periodic boundary conditions or not, or hard wall. We haven't seen. So, and now I think you will understand what is that this is of omega symmetric simple exclusion process. It is simply this thing here. Now, even on the level of the SSEP, you have a 2-state. In fact, you have a 3-state procedure. Did you get this here that we had so this was the configuration at time t. That was some intermediate state, which was not the state yet. And from that intermediate state, we got the configuration at time t plus 1. So now here, we have the same thing. Now in this example here, with probability 1/3, we say it's this puppy here that's going to be moving. With probability 1/3, we say it's this particle that is moving or that tries to move. With probability 1/3, it's this particle that we are trying to move. 1/3, 1/3, 1/3. Now we have a second state. Let me just say it like this. We have a second state is where we move either to the left or to the right. And that's how we come to a configuration. So we have 6 outputs, 6 possible outputs. Okay, so we choose particle 1. For example, we choose particle 1. Then with probability 1/2, we move to the left. With probability 1/2, we move to the right. In the SEP, if we cannot move to the right, then we stay where we are. If the move that we cannot make is rejected, then we stay where we are. Okay? So for example, let's say we choose to move this particle to the left. Then the next configuration is this configuration, then it's this configuration, 0, 0, etc., etc., etc. Okay, so that is the famous model called the symmetric simple exclusion process in a Markov-chain version, because this is at xt, and this, what I call here, is xt plus 1 of omega symmetric simple exclusion process. So what is known about the symmetric simple exclusion process? It is known that it has, okay, do you understand the model? You know, it's kind of, it's the basic of a lot of work. So it has been introduced by, yes? Well, no. We have n particles on L sides. So we have n particles on L sides. And what I'm saying is that the Monte Carlo algorithm has a lot of choice. So at time t, we choose which particle to move. Then we choose whether to move it to the left or to the right. And then we move, but it's called an exclusion process. So if I cannot move, then I stay where I am. All right? Okay, so now we can write down the transition matrix, but maybe in the interest of time, I'm not. So yeah, I don't know. So maybe we write down the transition matrix. It's going to be doubly stochastic. And there are different transition matrix for periodic boundary conditions, and another one for open boundary conditions. Okay? So now, let's lift this process. Are you getting it? Let's do, I mean, it's just, we try to generalize something that was written by famous people, and now we try to do the same thing, okay? So now let's lift this process, and how would we go about this? Who wants to write the paper? Gets you closer to your PhD. So what could we do? Yeah, but what is the same thing? You know, it's the same thing but different. So what do we do now? Yes, but then so let's say here there was already some operation on the level of the sample space. So now how do we change the sample space of the lifted symmetric simple exclusion process? Yes. So what we are doing here, see, is already getting a little bit more complicated here. So now, okay, so this is an xt of omega symmetric simple exclusion process. And now what do we do? So what we can do is we can say, well, everybody moves to the right or everybody moves to the left, okay? All right, so that's what we can do. We can do the following. We can say, we lift this like this, okay? All right, so now this is a lifted configuration, and then now, well, it's the same as here. Here I put the arrow on the particle, but it's just, I was saying that we are moving to the left, we are moving to the right. And so this is an xt out of the lifted symmetric simple exclusion process, and I call this simply the TASEP. It's called the totally asymmetric simple exclusion process. I'll explain that to you. Okay, so now we lift this in the sense that we say that at each time step, we don't simply move the particles. We don't move the particles in a random direction. We move them either to the left or we move them to the right. So, yes, that's the question. So, you know, we just pull out our pen. What we do? We come up with a procedure, and then we check. What do we check? That the transition matrix is what? Huh? Doubly stochastic. So anything that doesn't break up the double stochasticity is a good algorithm. All right, so what I propose to you is the following. We do the following. So we, for example, we have a configuration like this. Okay. So now let's do so let's say if we move this particle, yes? What do you mean? Like this? Like this? Yes? Well, let's see. I mean, the best thing is probably now I'm going to write down the transition matrix. Okay. So now what we are doing is the following. So let's take this configuration. So now let's say we are moving to the left. Okay. And then with probability 1/2, I move this one to the left. But now what I'm doing is if I move this to the left, it cannot move to the left. And following the procedure. Okay, so now okay, yes, okay. So let's do it like this. So from this one, we move, if we move this guy, we move it to the left, but we cannot. So then we say, then we are in this configuration. And then with probability alpha, we move the whole arrow again. All right, let's do it. Let's write it down. So now let me do it the following. Let me write it with walls. So okay, let me get a little space here. Let me get a little space. See, I'm trying to make as little, because there's some of in the audience that were concerned that I was getting lung cancer just because out of enthusiasm to teach to you from all the dust. So I'm trying to make as little dust as possible. So now let's do the following. Let me write like this. Configuration 1. Just as an example. Call this, and configuration 2 is the following. Configuration 4 is the following. And then configuration 5, I'm not going to write them down, all of them. Configuration 6. Okay? You understand? So I have the same configurations that I had already. So now I have 2 particles on 4 sides just to make things interesting. And now let us do the following. So now the transition matrix of the TASEP, which I call this the TASEP. It's not usually called this. What I'm doing here is not usually called the TASEP. The one with walls. So now you see if I'm at configuration 1. With at configuration 1, I am moving. I'm staying at 1. Then with probability here, I'm going to 3. But now what I should do is I should introduce a little alpha here. So with probability alpha bar, I'm staying at 1. So I'm moving particle right to the right. And then with probability alpha, I'm moving to the left. Then I can also move to 3. I can move this particle here with to 3. with alpha bar, and I can move it to 4 with alpha. So we can fill out this transition matrix here, and we will see that it is again doubly stochastic. And depending on alpha and alpha bar. So now, let us go back. Where were I? So I had the SSEP. What is known about the SSEP? SSEP. Known facts about the SSEP, it has a mixing time, and it has a relaxation time. And what is known? So let me take n proportional to L. We have n particles on the order of L on L sides. So it is now known that the relaxation time is n cube, and it is known that the mixing time is n cube log n. That was computed by a mathematician called Hubert-Lacroix in 2016. And the SSEP, this goes back a long time to Spitzer in the 1970s. So now we have done a lifting of the SSEP into the TASEP. We have a special version of the TASEP because we can go to the right, we can go to the left. And I may be not going into all the details. What you can do is in the following. You can, if you have periodic boundary conditions, you can restrict yourself to the TASEP only going in one direction. That's the one that is. So with periodic boundary conditions, but that's absolutely no necessity. You may restrict yourself to moves only go in this direction. For this case, there are famous results. The famous result number 1 is the tau TASEP is n to the 5/2 mixing time. That's a famous result by Baik and Liu, mathematicians from a few years ago. It's a really very, very well-known paper. And there's another result, which is the relaxation time, which is also n to the 5/2. And that's, for example, that is a famous result due to Deepak Dar, about whom we spoke just yesterday. Okay, so this is Baik and Liu. This is so now what you see, yes? We do exactly the same moves as we did before. Okay? Yes? See, that's exactly the discussion that we need, because you're not here to... Huh? Say it again. Maybe, maybe, what did you say? What was your question? The question was, how can in the TASEP, how can you reach this configuration? Well, not in one step, but well, in the TASEP, you just have to make sure that that the overall arrow goes to the right. then you move this to, then you have a finite probability alpha bar to move it from here to here. And then you wait a little bit until you have the arrow going in the other direction, and then you go like this. Hmm? Only one particle move. Okay, didn't I tell you? So only one particle moves. So here, okay, so here is you choose the particle that you move, and that particle moves in the direction that is given by the overall arrow. So there's a little paper that I wrote with Fabian Essler, who will come a little later, just last year. And in order to make this completely clear, we have lots and lots. We are complete specialists in LaTeX setup. So we have lots of transition matrix where you can actually check that this is correct. So the slightly non-traditional way is that we go in the right and we go to the left. So the point is, then we take one particle. Let me just resume. Okay. What's his name? Huh? Batza. So just so it is clear, so our algorithm is the following. We move the particles. If they are rejected, then we stay where we are. But if they are rejected at the wall, then we turn everybody around. Okay, so that's the algorithm. Okay, that's a perfect algorithm. And with periodic boundary conditions, we don't have a wall. And then we just move with a probability alpha. We move everybody with a probability alpha. Well, it is the optimal value of alpha is 1 over n to the 5 half. So it is known. It is a very, very, very small value. So you have to turn around in but let's not go into this discussion. So there is an optimal value of alpha. In fact, it's the value where you move most of the time. You move to the right, and then very rarely you move back to the left. So this optimal here in the sense of the prefactor of here. So now I'm throwing all these results at you without giving much details because it's just I cannot do that. But now there was so what is all this thing about? I'm throwing, as I said, I'm throwing all this result at you, all these results at you. But there has been a unifying principle. The unifying principle was introduced by mathematicians Chen, Lovac, and Pak many years ago, or a few years ago. So what they said the following. So unifying principle so that we can understand what is happening here. It is the following, that we have Markov chains. For example, the SSEP, and they're in relation, or the random walk, and they are in relation to brothers, to their brothers or offsprings. They call the lifted Markov chains. For example, for the SSEP, it is the TASEP. For example, for the random walk, it's the lifted random walk. And what are these properties? So we have a Markov chain and the lifted Markov chain. We have sample space and a lifted sample space, and we have a transition matrix and a lifted transition matrix. So what do they satisfy? So the following. So here we have a lifted sample space, which is in relation to an ordinary sample space. So the lifted sample space has the property that it has configurations x lifted out of x, and the sample space has x. And what it is, that every x is associated with a certain number X lifted 1, F lifted K. So you don't know. So what it is that we have, let me do it like following. So you have a sample space. This is omega. In omega, you have a point X. You have a lifted sample space. And in this omega, you have a number of configurations, X hat 1, X hat 2. You understand that this principle applies to the random walk and the lifted random walk, because we have one configuration of the random walk gets exploded into two configurations of the lifted random walk. It applies to the SSEP, because in the SSEP we have a configuration, and it gets broken up into two configurations at the moment. We'll go further. So now what they said in the following is the following. Maybe I don't want to go into too many details. So then also you have a transition matrix, lifted transition matrix, which is related to the transition matrix of the original thing. So the way it goes is the following. You have a configuration X bar X. You have a configuration Y bar Y, and X and Y. And maybe you have an element PXY. Okay? And in the lifted random walk, we have elements. We can go from X to this, and we can go from here. We can go from here, and we can go from here. And let's say if we have if the pi, and then what you have to satisfy is that the transition matrix between these two elements, the sum over these elements, and the sum over these elements. So the sum over pi p should be the same as the element from here to here. I can go into more detail. So now what they showed, is a theorem. Chain et al. Et al is, as we say in French, it's et al, but this et al is very, very beau linge. Is there any French speaking here? Are there any French speakers here? Yes, so c'est du beau linge. Ça veut dire it's really famous people which are in this et al. So what they proved is the following. Yes? So yes. So what I didn't tell you is the following. You don't have omega. You have omega bar, omega hat, p hat, and then you also have a pi hat, which goes to pi. Okay. And what you have to satisfy is that the sum over the pi hats of the offsprings of this here is the same as the pi of this one. And then what you have to satisfy is the sum over the flows of the offsprings is the same as the flow of the original. Yeah, exactly. So pi hat, p hat is the same as pi times p, okay? Between A and B, and the offsprings of A and the offsprings of B. Okay, all right. Okay, so now the theorem where I want to bring you is the following. Is that they say that this is a way, yes? No. We can also go, we can go here. We can go here as much as we want, that's not a problem. So that's not what is said, but let's say, so what it means is we are in a space, and from this space it has the original space of the random walk, lifted random walk, and we have probabilities, pi, stationary probabilities, and these stationary probabilities, we find them back up here. The transition matrix, we have a transition matrix, we find it back up here, and we could have studied that in the thing. So now we have a number of results. That's what I want to show you. It's really interesting. It's really interesting. First of all, if you know what is a conductance of a Markov chain, we can discuss that in the break. But first of all, the transition matrix of the lifted random walk, the the tau of the lifted random walk must be larger than the square root of tau of, of the lifted Markov chain has to be larger than square root of the Markov chain. I'm giving you in some sense, I'm giving you simple versions. So this is, and the tau is for the relaxation and for the mixing. And it's also here for the relaxation and for the mixing. So this is simple version, okay? It's like Wikipedia, you know, there's English and Wikipedia in simple English. So I'm giving you just the upshot of what we are doing here. So what they were telling you is you can, for example, in the lifted random walk, we went from a relaxation time, which was L square, to a relaxation time, which was L for the lifted random walk. And they said, well, this is completely general. You cannot do any better. Second thing that they said is you have to go from reversible. So if the random walk is a reversible, you have to go to a non-reversible. So this gain here can be obtained only if you become non-reversible. So is the lifted random walk non-reversible? Yes. So if you stayed in the world, which is the world of 99% of the Markov chain of research, then you cannot gain anything. So this is kind of, I can spend endless time discussing these two results here, first of all. For example, because this is a very general result. I can, as I said, I have lots of things to say about this. And it shows that there is so we call this like this, there's you think you are the president, but I was just going to propose you so he's going to be president for life. You know, that's very dangerous, right? We are going, you know, now you have the second term, it's, you know, third term. And so, okay, so in 5 minutes I stop here. So now, if you look at this here, this is like going from diffusive to ballistic motion. Okay, so then what they told us is that you understand there's the diffusive motion in particle systems, and there's diffusive motion and there's ballistic motion. One is it has a velocity, and the other one has no velocity and has only diffusion. And the difference between diffusion and velocity is exactly the factor of square root. So these are profound results. In my humble opinion, they have not been studied at all at the level that they should be held. But now, what I'm driving you at, or what I'm coming to, is, you see here, this is the SSEP, which has an n cube log n and an n cube. Let's forget about the n cube log n. And here we have n to the 5 half and n to the 5 half. So it satisfies this thing. But the question, of course, is, can't we do better? Okay? So here, the TASEP, just to say, goes like n to the 5 half. And you agree that this is larger than the square root of n3. I'm forgetting some logarithms. Okay, that is true. But what they tell us that if you work a little harder, then maybe you can get to the n to the 3 halves. No. I'm just saying that you know, then maybe it gives us hope. So let's put it this way: when we started this kind of algorithms, we had absolutely no hope that making a change of a local algorithm would improve our things. You know, we just wrote algorithms in 2D, 3D, 4D, whatever. You know, and then we noticed that this algorithm became very, very fast. Then we talked to our mathematician friends, and they told us, well, you know, look at these papers. You can improve the scaling of relaxation times. So this algorithm, do you understand the following? Did you understand the following? The TASEP, the SSEP, is a local Markov chain. Local meaning you move one particle at a time. The TASEP is also a local Markov chain. You move one particle at a time. But they have different scaling. So in the limit of n going to infinity, one is much better than the other. So now what I'm just saying is, so the TASEP is, so this is true. So this is true. So this is the square root of the SSEP. But maybe we can do better. Okay? So now, the way we can do better, yes? That's a theoretical bound. No, I mean, that's what you can work on. I mean, you know, when we are back at home, we can, but so I don't think there is a proof that it always exists. But then when you have an algorithm which is doesn't satisfy, then you all of a sudden you sit down with a cup of tea and start thinking. Right, so that's what I'm going to explain to you. So now, where is the key to where we can still obtain codes is that the lifting I was explaining to you from the SSCP to the TASEP was incomplete. Because I only had a lifting in the direction of where I was moving, and I'll tell you the rest of the story after the break. Apologize that I'm not telling you everything I would like to explain to you. For example, now in the break, there was a question: how does what I'm doing here comparing to Hamilton in Monte Carlo? Some of you know this. What is this field of Hamilton in Monte Carlo? And I'm very much interested in that. I would have studied it. So a few years ago, just to make the link, a few years ago I was invited by my friends to University of Tokyo, and I gave talks. And the format here was different from here. So it was 4 days, just like now, but 32 hours of lectures. So then I was doing 8 hours a day, and then afterwards everybody was completely essoré. And then we had to go. To izakaya and have a lot of sake to get. But then you know, under this format, I would have told you everything that you will ever need to know about Hamilton in Monte Carlo. But now we have to make a choice, and the choice was that I did not talk about Hamilton in Monte Carlo. But now, what I was trying, so I'm getting you into this world of lifted Markov-chain. One of the reasons why I think it's very interesting is it's, in my opinion, not sufficiently explored. But let's continue with our story. So we understand that we have this limit. So it is lifting. It means we have our original sample space gets enlarged. We have more configurations. But finally, we don't make much of a change. And the reason why it's so interesting is because nobody was, so we were believing that one of the reasons why nobody worked on non-reversible Markov chains is because it was so difficult to set them up. So it's just not, you know, you have this condition, pi is equal to pi p, okay, all right? So, you know, the professor talks to the students, say, find an algorithm. You know, how do you find the algorithm? It's very difficult. It's very difficult, and this lifted Markov chain give us a possibility. So now in the SEP, you understood that from the SEP to the TASEP, we have increased the sample space by a factor of 2. So we have you know, 2 configurations, but now we can go even further. And so what I'm going to explain to you is something that which is which we analyzed, which I have been studying for a few years, for many years, but which we fully analyzed with Fabian Essler, who will come a little later. So now what we do is the omega lifted TASEP. So let's say for the lifted, so let me do it like this, lifted TASEP. So now let us take the version of the TASEP that is more the original version. We have particles. And the TASEP is the following. We only move in the right direction, just for simplicity. Okay, so we take the TASEP as it is usually performed. So we move only in the right direction. We have periodic boundary conditions. And if we reject the move, if a particle cannot move, we reject the move and we stay where we are. So this is the TASEP. So it has an omega TASEP, which is, well, it is 1/2 of the TASEP that I discussed before. And in some sense, it's 1/2 of a lifting of the SEP. So now what we do is the following. We cut this up, and there were a number of you already proposing this. We cut this up into n configurations, so we have n particles on L sides. And the way we do it is the following. It's either this particle that's moving, or it's this particle that's moving, or it's this particle that's moving. Now let me explain the moves. Oh, excuse me. So let me explain the moves. It's the following. So you have a configuration. It's like this. So that is x of time t of the lifted TASEP. I still find it amazing, even though I've been thinking about this for a while. I find it amazing that the same framework that we applied, and you'll see it. So that's the intermediate state, okay? That's the intermediate state, just as we had it for the lifted random walk. And now what we do with probability alpha, we turn it around. And with probability alpha bar, we don't do anything. Okay. And now let me give you another example. So what do we do if we have a collision? Okay, so now we have this here. That's also a configuration of the lifted TASEP. And now what we do, the intermediate. Okay, now comes a little subtlety. So what do we do now? We move like this. So we do a collision. That's like in Hamiltonian. That's why we are interested in Hamiltonian Monte Carlo. We go like this. And then with probability alpha, what do we do? Huh? No, because then we would have a configuration that we don't have in the TASEP. So we are taking the TASEP that only moves to the right. So we cannot flip it. We cannot flip it back because that gives us a configuration that's not present in the. So I'm doing a lifting of the TASEP that only moves to the right. So I have to stay with things that move to the right. So now with probability alpha, I transfer it to the previous guy. And with probability alpha bar, I stay where I am. Speak up. Oh no, I didn't flip the arrow. No. No, excuse me. No, I just moved the particle. No, excuse me. No. Excuse me. Thank you, thank you. Okay, I was just, so with probability, excuse me. So with probability alpha, I take it back to the previous guy here. So I'm moving here. I'm taking it back. Excuse me. I was a year elsewhere. Okay, so with probability alpha, I move it back to the previous pi and this. So now this is actually the thing. So now here is also xt. So I move the particle forward. I make a collision, like in Hamiltonian Monte Carlo, and then I stay here or I move it back to alpha. So now what I can do is I can write down, let's make a little example. Let's do it. Maybe I have enough space here. So I take configuration. I just take two particles on four sides. So this is configuration 1. Configuration 2. Configuration 3. Configuration 4. Configuration 5. Let me just go through here. I think I'm really also I'm also a little tired here. Configuration 6 and so on and so on. And so on and so on. So now the of the lifted tacep is the following. So let's just do it. So with probability alpha, so from this configuration, I move the arrow to this guy here, to 2. So I have 2, which gets an alpha bar. Did I say alpha bar? Yes. So I go from here and stay there with probability alpha bar, but then I pull back the arrow and I have alpha. 0, 0. And let's do it again for configuration 2. So from 2, what do I do? So from 2, I move this particle over here. So this gets for 4. So I get an alpha bar here and an alpha 0, 0. Let me see. From 2, I go to 3 in my opinion with alpha. I go to 3 with alpha and alpha bar. So from 2, I go to 4 with alpha bar, and I go to 3 with alpha. Okay? Yes? From now on, yes, I can do that. It is in some appendix gamma of what we are doing. But let's say from now on, what we only consider, so I take 1/2 of this thing here. I only take this copy, and I take 1/2, and I continue with this. Now I have a periodic boundary condition. I have periodic boundary conditions, and so I can also move like this. All right, so this thing here is, again, it has alpha, alpha bar, so it goes like this. It is a stochastic matrix, and it has this little boxes alpha, alpha bar, just like we had them before, and it is also a doubly stochastic matrix. So all configurations have equal probability. So the question was posed in the break. the question was posed in the break. Don't we get a problem? Don't we get a problem if we increase the sample space too much? Right? And the answer is not really. So now, okay. So now the lifting is the following. We are so the lifting. So the lifted TASEP has a omega of the lifted TASEP is n times then the omega of the TASEP. And if we did this, with respect as you proposed, we keep the right going to the left going, then we would see that the TASEP is a lifting of the SEP, and the lifted TASEP is a lifting of the TASEP. So it's a pyramid going through. So now, what I want to end up with is the following. I want to show you what is happening. So now so this is the active. So this particle here is the active particle. Okay. So now in this model, in this lifted TASEP, we have two types of transport. First of all, we have mass transport. So that means if we look at the configuration at time t and the configuration at time t plus 1, we'll have moved the particle or not. So we move particles. So it is between t and t plus 1, we have moved a particle to the right, or we have not moved the particle. So let's say if we have n, for example, we have n anyway. So we can move particles in the limit of n going to equal to L. We have a limiting mass transport. But the second also, we have a transport of which is a drift of the active particle. So we have so if alpha is equal to 0, then the transport of, then there is not much difference. But if alpha, so it is, that is governed by alpha. So now, so what I mean by this is that if alpha is very large, then I have a very high probability to move the particle back. You see it here, for example. I started with the active particle here. After a move with probability alpha, I have the particle that I have the active particle back. And let me write down one formula here. The drift of the active particle, let's say of the active directivity, what is it? It is the position of the active particle at t plus 1 minus the position of the active particle at t with periodic boundary conditions. So I take into account period. It is equal to 1 with probability alpha bar. So you see it here that if with alpha bar I move, so here I had the active particle, the arrow, I had it, the pointer, I had it at position 2. And at the next time I had it at 3. So this was 2. This was 3. In this configuration, I had the active particle at 2. And here I have it at 3. So this is a correct formula. The difference is xt plus 1a minus xta is 1, if with probability alpha bar. And it is minus L minus n divided by n with probability alpha. Putting them together is that the expectation, the mean value of the so the pointer position at time t minus the pointer position at t plus 1 minus t is 1 minus alpha times L over n. So now I'll finish in 2 minutes, and I go into an overview of how this fits all in. So now, okay, you understand what I'm doing? I'm just computing where is the pointer at time t. I'm computing where is the pointer at t plus 1. And I see that there is a dependence on alpha. So the mass transport is almost the same. But then the pointer will be having a drift. So this is the velocity, the expected velocity of the pointer, excuse me, is given by 1 minus alpha times L over n. So if alpha equals to 0, then the velocity is positive. If alpha is equal to 1, then the velocity is negative. Okay, so you see that? And there is a sweet spot where the velocity goes to 0. So at alpha equals to n over L is alpha critical. The velocity is 0. So I have analyzed, okay, you understand that? So it's the velocity of the, so I'm moving particles, the particles are moving to the right. And then with a certain point, I'm moving the pointer to the left, I'm moving the pointer to the right, and so on and so on. So, but I have a special point. It would be very surprising if that special point was not the special point of the algorithm and was not the one that was giving me optimal convergence. So I'll show that now at the end. Let me do the following. So I have a lifting of the TASEP, calling it the lifted TASEP, where you have a pointer for each particle, okay? And this for a particle, so one particle has a pointer, and this pointer assures transport of mass, but then the pointer itself moves, and it moves with a velocity which is given. So the pointer moves with a velocity which is, now I want to get to some formula, 1 minus alpha divided by L over n. So that is the ensemble average of pointer motion. So now, for alpha is equal to n over L, velocity is 0. So now we get back to the question, so what is going to happen? So how long will the pointer take to move through the system? Well, of course, in the system going to infinity. So what? Of course, it will be a function of L. So what is going to be the function of L? So you would expect, because it has no drift, you would expect that it's L square. That's a naive guess. Yes, yes. You don't have to take out an insurance policy before making this guess. Okay. So now you have at alpha. So what is happening? You have this system going from 0 to L. You had periodic boundary condition, and you look at the configuration as it moves. So now what I'm going to tell you is so then you have a special point at which the pointer motion has no drift, so you would expect it to be diffusive and to move like L square. Now I'm going to tell you the following. So now let's take a configuration. So there's a configuration of this. So the pointer is here. Okay. So now let's coarse grain this this area. So what I'm showing here is that so let me write this here. So the velocity of the pointer on some coarse-grained. So I'm just taking this equation, which is a true equation that we can derive. I'm writing the coarse-grained velocity of the pointer. So now I multiply with n over L minus alpha divided by n over L. You agree that this is a correct formula? It's the same as this one, right? L over n. So now what I'm doing is the following. So this would be now I'm saying I am at a configuration. In the configuration, I have n and L. So this is rho bar. That is the mean density. But I have a possibility that in my system, I have a density which is different. So let me say that at position X, I have a density which is rho averaged over some little length scale L. So let's put this in here. So this is going to be rho bar minus alpha divided by rho bar. Or okay. So but now let me say the following. So if I have a density L, then this will be rho, this will be rho, and this minus alpha. You understand? This formula is correct if this is the mean density. So this is rho bar divided by rho bar minus alpha. But now I'm saying my pointer is moving in the density rho, and then this velocity here, the velocity at time t of my pointer is given by some coarse grain density rho L minus alpha divided by rho L. So now let's do the following, and I stop in 2 minutes. Let's do the following. Well, we'll justify it later. We'll justify it in 2 minutes. So I'm just saying, I am in my pointer. My pointer is at some local density, which may not be the full density, but it's at some density. And now let's put alpha to be alpha critical. So now the density coarse-grained over length scale L. What is it going to be? It is going to be the rho L. And now let me take the alpha critical at alpha critical minus rho bar divided by rho L. So what is it? Delta rho L divided by rho L. So delta rho L is rho L, delta rho L is equal to rho L minus rho bar. So this is a fabulous formula. I come back to, this is a fabulous formula. What I'm telling you is if the local density is a little higher, you know, I have a configuration. If the local density is a little higher than rho bar, then the velocity is positive. If the density is a little lower than rho bar, then the velocity is negative. So this is something that we can use very quickly, very efficiently to compute. For example, I show you compute mixing times in this system. It's also very, very useful to do an equilibrium analysis. So what is going to be, so now question, what is going to be the delta rho in equilibrium? I have n particles on a length scale L. What is going to be the fluctuation? It's 1 over square root of L, right? So we'll have in equilibrium, rho bar will be 1 over square root of L. Square root of L. So I have a process. Even in equilibrium, it will have velocities that pick up the fluctuations of the density. If the density is a little higher, it moves to the right. If the density is lower, it moves to the right, to the left. So what is going to be the time scale for the pointer motion through the system? Well, I mean, I put n equals proportional to L. Okay, I put n proportional to L. Then I have a central limit theorem fluctuations of the density. So these fluctuations will be 1 over square root of L. So the pointer motion through the two systems, what is going to be? You have a velocity which is 1 over square root of L. You have a distance to move, which is L. How much time does it take you? Exactly. Thank you. So now where did we start? We started with the SEP. The SEP had a relaxation time of n cube. And all of a sudden we see that there is an n to the 3/2 coming out of our system. Right? I mean, I mean, I have not told you anything. I'm just telling you that naturally at alpha, so this is at alpha at critical alpha, you have a process which has a zero diffusion, zero drift, but it's not diffusive because it moves through the system on a time scale L to the 3/2. It will see the whole system in L to the 3/2. This L to the 3/2 is the square root of L to the third, which is a very, very fundamental principle which comes out of famous mathematical papers from 1999. So we see this thing here. So now, you understand the point? You understand what I'm telling you? So I'm saying we have a process. We have the SEP or the TASEP. But now we're not like in the TASEP where at each time step we take a random particle and move it. Random particle, move it. It's just kind of stupid to do that. What we are doing is we are moving one particle at a time. Now we have a process that who is moving corresponds to a second equation. So we have the mass transport equation up here, and we have a transport equation for who is going to move next. Who is going to move next? We can go back into the boring limit of the TASEP. We get also the same scaling as the TASEP, is when you move one and then the next, and you don't look who is moving if you have a drift. But there's a much more interesting point. It is the one where you don't have drift. Does not having drift mean you have diffusion? No, because with this little equation I showed you, we have a coupling. We have a coupling of the pointer motion to the local density. This local density has fluctuations. There's 1 over square root of L. So the time it takes to go through the system will be L to the 3/2 and not L square. So this was first worked out in other famous mathematical papers by Wendelin Werner and Balin Todt in the late 1990s. It is related to a famous physical process called the true self-avoiding random walk. And that's where this thing comes out. So now the final point I want to make is that this model, working together with Fabian, who is going to come in very quickly, is also Bethe-Ansatz solvable. So it means that so we were extremely happy to find out that this model we have a transition matrix, and this transition matrix we can get eigenvalues. At the moment, it's still very it's a lot of work. I mean, it's a lot of work, and so we can get individual eigenvalues of this transition matrix, and this works kind of agree and contradict with this L to the 3 halves. So we have a single state in our system which still scales like L square, and we are continuing to work on this. But this L to the 3 half, as I showed you here, comes out a lot in numerical simulation. It's the square root of L to the 3, which is the time scale of the SAP. Yes? That, formally speaking, is the motion of the pointer particle. And we think it's the relaxation time. There is the relaxation time, except for one state that we. So this is still. I'll come back next year to tell you all the story about this. But we have a time scale which is L to the 3 half, which is the time scale on which the pointer goes through the system. And as we say in the French Revolution, you know, there was something called the French Revolution. It's not just the Markov-chain revolution. Morally, you know, morally, the L to the 3 half is the relaxation time of the system. So it obtains, so this lifted TASEP gives the optimal lifting of the SSEP. Yeah? Yeah. It's the transport through your system. No, it is. So what comes out of it is that the mass transport, so the relaxation of density fluctuations, also relaxes morally, I have to say, morally on this time scale L to the 3 half. Two liftings. Yes. Yes. It's always, you know, it's kind of course, I wouldn't be telling you. So now, what is the? So that, of course, now it's a question of whether it works for other. So now, at least we have one model where we can follow, where we can have a beta ansatz, where we can have a full control, and we actually control what we are doing. Now, if we have, but I think we don't have time. I can explain to you how these algorithms. So this is a Monte Carlo algorithm that I'm telling you, right? It's a random process that we can study in one-dimensional physics. It's a one-dimensional physical process, but it's also a Monte Carlo algorithm. So does this Monte Carlo algorithm generalize to n particles in three-dimensional space and so on and so on? Okay, that's the question you're asking. And does it speed up our motion? The answer is yes. But we don't, of course, we don't have a beta ansatz to, we don't have strong numerical results. I mean, we have strong numerical results that these algorithms are much better. But let's do it like that. Let's do the following. I mean, if we still have, no, but yeah, anyway, so, bitte? We can do it in the discussion. But let me just tell you, the following, and then that's my final word. So we have an algorithm which is called the lifted TASEP, where you have one particle which is the active particle, and it moves, and it has two possibilities like this. Okay, so this is the configuration at time t. At time t plus 1, you are here. Now, so what I actually do to make a living, okay, because you know physics is our passion, right? But it's also good that we get a little salary, so that we can buy butter. So you know, butter, milk, diapers, and all of this. So now let's say we have particles with arbitrary interactions. So your question is, can I generalize the lifted TASEP to an arbitrary model of water molecules interacting with polymers, and you know, I mean, so in real, can I work? And what I'm telling you, it's the same. So what you do is you take a single particle, you move it forward, you move it forward. Let's take the case alpha equals to 0. Let's move it forward. Let's move it forward. Let's move it forward. You can also do it for alpha. Let's move it until it hits. When it hits, it's going to be this particle. So the configuration is going to be this one. And it's this particle that's going to move forward. Okay, so I'm not going to start a whole new chapter of our lives in the last 5 minutes. But what I'm telling you is, of course, everything I have tried to explain to you is Markov-chain Monte Carlo algorithms that are of general validity. The most general algorithm is, of course, the Metropolis algorithm that I think many of you have programmed. But there is a whole world of new algorithms that have come up since, whole new world of new understanding, which started 1986 with the mixing time and relaxation time analysis of Aldous and Diaconis. There is a whole new bag of algorithms. Are they useful? Are they not useful? In any case, it's different. So it saves us from boredom to do exactly the same thing that everybody has done before. And they have tried to solve problems. So it gives us a whole new space of algorithms. So today I explained to you a one-dimensional lattice reduction, because here we are in a workshop where a lot of work was on one-dimensional quantum systems or one-dimensional systems. So there is a one-dimensional lattice reduction of our favorite algorithms. These algorithms are called event chain Monte Carlo, whatever it means. And it again shows that in some sense, it's an optimal algorithm. It's an optimal algorithm in the sense that the TASEP is not an optimal, non-reversible algorithm. So with this, I think up to the discussion that we'll have later today, I leave you and I wish you all the best for your thesis and postdoc and what you're doing. And you know my phone number and you can always call me. Okay, and so thank you for your attention.